In this particular diagram, on the upper part, we see the absorption of the incoming incident electromagnetic radiation that's interacting with the atmosphere over the wavelength region, going from zero point 0.1 micrometer out to 30 micrometers. So that's a very long wavelength range on the x-axis there. And we have absorption going from 0 to 100 on the y-axis of those little subplots in those multiple top figures there. And then on the bottom part in general, we see the combined effects of atmospheric absorption, scattering, and reflectance. So in the upper figures, we see the absorption characteristics that are associated with N2O, O2, and O3, carbon dioxide, as well as water vapor. And the very bottom graphic in the upper set of slides in part A there of the figure is the combined cumulative results of all of those atmospheric constituents combined into one plot, operating within the atmosphere at one time. And so it shows that the atmosphere is basically closing down in certain portions of the spectrum, whereas we have atmospheric windows in other regions of the spectrum, again, effectively transmitting that incoming radiation down to the ground surface. And again, that's where we're going to be concentrating our remote sensing efforts. And the combined effects down on the lower graph basically of the absorption, scattering, and reflectance processes basically reduce the amount of incoming solar irradiance. It's basically radiation that's traveling in all directions, but actually reach the Earth's surface at sea level is what we see in that bottom figure. And also note, you can see the individual absorption regions pretty clearly due to various atmospheric gases and constituents. And this particular slide is just showing the same thing that we had in the previous slide in the upper portion of the figure, just in a little bit more detail. Again, breaking out the absorption profiles for N2O, O2 and O3, carbon dioxide, CO2, and water vapor H2O. And again, the kind of white areas down on the bottom part, and this applies to the upper figures as well, but the white part are atmospheric windows, the combined effect of those gases, and the dark parts are basically areas where the atmosphere is shut down, where we do not want to do remote sensing. Another important process, again, that operates on electromagnetic radiation is reflectance. And I alluded to this in a prior slide, and that is the process where the radiation basically bounces off an object. It could be a cloud, or it could be some material type on the Earth's surface. The actual process is more complex than that. It involves re-radiation of photons in unison by atoms or molecules in a layer that is 1/2 of a wavelength deep. And reflection basically gives us information about various characteristics of a particular type of material, and it is a very important quantity in remote sensing. So you should be very familiar with this particular process and the associated quantities. And some of those important characteristics are as follows. Number one is that the incident radiation, the reflected radiation, and a vertical or a normal to the surface from which those angles of incidence and reflectance are measured all lie within the same plane. Okay? And secondly, the angle of incidence and the angle of reflection are equal to one another. And there's different types of reflecting surfaces. One is a specular reflector, and that is where we have radiation that's being reflected off a very smooth type of a surface. It's basically one where the average surface profile is several times smaller than the wavelength of the impinging radiation that's striking the surface. Another situation is if we have a somewhat rough surface, we can have what is referred to as diffuse reflection that is occurring. And it doesn't give us a mirror image, but it basically generates diffused radiation. So things like white paper or white powders, other types of material basically are going to be reflecting light in this type of diffuse manner. And then we can have the situation where the surface is so rough that we don't have any individual reflecting surfaces. We may have scattering that's occurring. And Lambert basically defined a perfectly diffuse type of a surface. And we commonly designate such a type of surface as a Lambertian surface. And that's where the radiant flux that is leaving the surface is going to be constant or isotropic over any angle of reflectance that's going to be normal to the surface. So in this diagram, we see the case of a perfect specular reflector in the upper left-hand corner, whereby the angle of incidence exactly equals the angle of excidence, and it's basically acting kind of as a mirror type of a surface. With a smooth water surface being an example of a perfect specular reflector. We have a near perfect specular reflector in the upper right hand corner of this figure. But there is a little bit of roughness to this surface, so the angle of excidence, even though it's predominantly in one direction, there are some other vectors for the angle of excidence for some of those photons being reflected from that surface. In the lower right-hand corner, we have a perfect diffuse reflector, or what we refer to as a Lambertian surface. And really, with that type of surface, we're going to have, again, if it's perfect, we're going to have equal reflectance that's going to be occurring over really the whole 2 pi hemisphere over that surface. And then in the lower left-hand corner of this figure, we see a near perfect diffuse reflector again. We have a lot of vectors traveling. It's not equal again, but it's kind of more or less equal, although we do have a few directions where we have a dominant kind of angle of excidence for a significant proportion of those photons. So we should note that Lambertian surfaces are often used as an approximation of optical behavior of objects. However, we should also note that the Lambertian model does not hold exactly for most natural surfaces. In reality, there are complex patterns of reflection as a function of the surface geometry, and some surfaces exhibit Lambertian properties at some angles of incidence. But they might exhibit clearly non-Lambertian properties at other angles. And so we should note that reflectance properties of a surface are characterized by what we refer to as the bidirectional reflectance distribution function, or the BRDF, which I've referred to in a prior lecture. And what we see here in this figure are the BRDFs for two different types of surfaces. We have it discretized, these surfaces over the whole 2 pi hemisphere into different sectors, if you will, and the different shadings are basically corresponding to different reflectivities in that various portion over the 2 pi hemisphere over a particular type of target or material. So to be specific, we can define the BRDF, the bidirectional reflectance distribution function, as follows. So it's a mathematical description of the optical behavior of a surface with respect to both the angles of illumination and observation, given that it has been illuminated with a parallel, or what we might say collimated, beam of light at a specified azimuth and elevation. Okay, and the function here, this BRDF, is bidirectional in the sense that it accounts for both the angle of illumination and the angle of observation. So in other words, it's accounting for the sun, if the sun is the source of our illumination, the sun target sensor geometry. Okay, and the description of BRDFs for actual rather than just these hypothetical idealized surfaces enables us to assess the degree to which the various types of surfaces approach, an ideal or perfect specular reflector or a diffuse type of a surface. I should also note, related to this concept, and I noted Lambertian surfaces, we try to uh, approximate a Lambertian surface when we are making spectroradiometer measurements. We want to compare the measurements that we are making, which are in units of radiance, by the way, which I will define here shortly. And if we want to compute or derive from that quantity units of reflectance, we would use a Lambertian reflector or a reflecting surface that approximates a Lambertian reflector. And typically, one might use a material like Spectralon. That's not an endorsement for that particular type of material, but I just mentioned that as a commonly used type of material that we would use for making such types of measurements. All right, so I'm next going to be focusing on terrain energy matter interactions. And we should note that the time rate of flow of energy that is onto, off of, or propagating through a surface is referred to as the radiant flux, and we measure that in units of watts, which we denote with capital W. And the characteristics of the radiant flux and the fate of that as it interacts with the Earth's surface is very important in remote sensing. That gives us critical information about the properties, whether it be biophysical or whatever, of various types of materials or objects. And this is really a primary focus of a lot of remote sensing research. So if we carefully monitor the exact nature of the incident or impinging radiant flux in various wavelengths and how it interacts with the terrain or various types of materials, it may be possible then to learn important information, again, about the terrain or different types of Earth surface materials. So radiometric quantities are, of course, very crucial in remote sensing in that they allow us to basically keep track of the incident as well as the exiting radiant flux from a surface or particular material type. And so what we refer to as the simple radiation budget equation basically states that the total amount of radiant flux that is incident onto the terrain or some type of surface. In this case, we denote that with the capital I sub lambda. And the lambda for that quantity and all of these quantities is denoting that it is wavelength dependent. Okay, so for the radiant flux, the total radiant flux that is incident to our surface, we need to account for that by evaluating the magnitude of energy that is reflected from the surface, that's little r, the magnitude of energy that is absorbed by the surface, that's alpha, and the amount of radiant energy that is transmitted through the surface, that is our tau value. Again, all these are wavelength dependent. So the sum of r, alpha, and tau is going to equal the energy that is incident to that particular surface. We should also note that radiometric quantities are based on the amount of radiation that is incident to a surface from any angle within our hemisphere. That's that 2 pi hemisphere that I was referring to over a particular type of surface. This slide is essentially the same as the previous slide. It's just that the notation here is a little bit different. But again, we're representing the radiant flux as a function of that which is reflected, absorbed, and transmitted, and equaling that to which is incident on a given surface. But I just included this slide to show that different notation is possible. So in terms of some other radiometric quantities of interest in remote sensing, one is the hemispherical reflectance, which is rho sub lambda here in this figure. And that is a dimensionless ratio of the radiant flux that is reflected from a surface to the radiant flux that is incident to it. So reflected over incidence. Another one is the hemispherical transmittance, or tau, and that is again a dimensionless ratio of the radiant flux that is transmitted through a surface to the radiant flux that is incident to it. So again, we see tau being computed there. And the hemispherical absorptance, again, this is alpha, and it is the radiant flux that is absorbed over the amount that is incident to it. The hemispherical absorptance, again, that's alpha. It is defined by this relationship, which again is dimensionless, that we see here. So alpha equals 1 minus this quantity, which is the sum of r plus tau. And this basically tells us that the radiant energy must be conserved. And what we mean by that is that the energy is either going to be returned back by reflection, it's going to be transmitted through this type of material that we're dealing with, or is going to be transformed into some other type of energy inside of the terrain. And the net effect of absorption of radiation by most types of materials is that the energy is going to be converted into heat, which yields a subsequent rise in the temperature of a given material. Now, if we take our simple hemispherical reflectance equation and just multiply that quantity by 100, we're going to get the expression for percent reflectance. And here we denote that with rho sub lambda, and this is going to be in units of percent. And all we do, again, is take the radiant flux that is reflected from a surface divided by the radiant flux that is incident upon that surface. Again, these are wavelength dependent quantities. We multiply that quantity by 100, and that yields our percent reflectance. And this is a very important quantity in remote sensing research because it enables us to describe spectral reflectance characteristics of various types of phenomena. And with remote sensing, we are essentially doing remote chemistry. So with spectral reflectance curves for different types of materials, those data enable us potentially to estimate various biochemical, biophysical properties of various types of Earth's surface materials and various types of objects. So it is an extremely critical and very commonly used quantity in remote sensing. In this figure, we see spectral reflectance curves for various types of urban-suburban types of materials over the wavelength region going from 0.4 to 0.9 micrometers. So specifically on the x-axis, we have wavelength in units of micrometers, again going from 0.4 to 0.9 micrometers. And on the y-axis, we have values of percent reflectance, which we showed how to compute on the previous slide. And plotted on here is various spectral reflectance curves for various types of materials. And we say spectral reflectance curves because we have reflectance values, percent reflectance values, that are computed in multiple portions of the electromagnetic spectrum. And on this graph, we see these kind of smoothly undulating continuous curves. These would be basically hyperspectral data plots, just because we would have many data points, or basically data that are collected in hundreds of bands, in order to yield these very smooth spectral curves. If we had a multispectral sensor, maybe with 4, 5, 7, 8 bands available to us, we would have the same sort of information. It would just be more generalized, kind of more jagged looking reflectance curves that are plotted. Anyway, what we see here are various types of materials plotted. We have percent reflectance values for grass, a fallow field, soil, concrete, various building materials, asphalt and water. Those are low reflectance values across much of the wavelength range there. One thing I'll point out is that we have very similar values over the visible portion of the spectrum, or at least part of it, for grass, or a good portion of it for natural grass, as well as artificial turf. It's really once we get, though, into the longer wavelengths, especially the near infrared portion of the spectrum beyond zero point 0.7 micrometers, is where you see a massive divergence between artificial turf and grass. So artificial turf to the naked eye looks green. It approximates green grass, right? And green has higher reflectivity. Uh, Grass has higher reflectivity in the green portion of the spectrum and higher amounts of absorption in the blue and the red. And likewise with artificial turf. So it kind of mimics what artificial turf mimics what grass would look like to the naked eye in the visible portion of the spectrum. But if we have a remote sensing device that is sensitive to the longer wavelengths, we really see a divergence in those spectral signatures. So if we want to discriminate between artificial turf and grass, we would really look predominantly to the near infrared portion of the spectrum. Because we have the greatest differences between the spectral reflectance curves in that region of the spectrum. And so for that reason, this particular graphic really summarizes a lot of what remote sensing is about. Not all types of remote sensing, but this particular type is about. And that is in different portions of the electromagnetic spectrum, we have varying amounts of contrast or differences between these reflectance curves for different types of material. So if I want to discriminate between different types of materials, I can tell from this particular type of plot what wavelength regions I would want to collect information in or collect data in to be able to tell the difference between these different types of materials. So what we're seeing in this figure is a further illustration of one of the things I was talking about in the prior slide. And specifically, we see wavelength on the x-axis in units of micrometers, and the wavelength range is spanning from 0.4 out to beyond 0.8 micrometers in the near infrared portion of the spectrum. And on the y-axis, we have values of percent reflectance. And specifically, we have plotted on this graph spectral reflectance curve for vegetation, as well as a reflectance curve for a first generation camouflage type of material. And by first generation, we mean that it does not replicate well the reflectance characteristics of vegetation out in the near infrared portion of the spectrum. And we can see that here by the great divergence between the reflectance curves for camouflage, which is this lower plot, versus vegetation, which is the upper curve there. And as we talked about previously, healthy green vegetation has very high reflectivity in the near infrared portion of the spectrum. And the reasons for that we'll be talking about in the remote sensing of vegetation section later on in the course. But the main point here is that with camouflage in the visible portion of the spectrum, at least with this first generation type camouflage, it replicates well what vegetation looks like. So we have a reflectance peak here in the green portion of the spectrum. We have more absorption in the blue and the red, just like healthy green vegetation has. But again, this first-gen camouflage did not replicate the reflectance characteristics of healthy vegetation in the near-infrared well. So if we wanted to try to detect camouflage, for this type of camouflage, one would opt for a particular sensor that had sensitivity in the near-infrared portion of the spectrum. And you would see, again, this great divergence between the spectral characteristics of camouflage and vegetation in that portion of the spectrum. More recent versions of camouflage do a much better job of mimicking reflectance characteristics out beyond the visible wavelengths. There's other types of camouflage, optical sorts of camouflage, which kind of try to mimic in a way invisibility processes, which I'll talk about later on. But anyway, there's various types of next-gen camouflage that can be employed. But this is a good illustration of the principle that I talked about, basically using multiple portions of the electromagnetic spectrum, especially wavelength regions outside the visible, to discriminate between different types of objects. Irradiance and excitance are important quantities in remote sensing. The amount of radiant flux that is incident upon a surface per unit area of that surface is referred to as the irradiance. We denote that with capital letter E, and that is basically a universal symbol that we use in remote sensing for that quantity. And we again summarize it here, the incident radiance over a particular area. And recall that the lambda subscript there again is referring to the fact that this quantity is wavelength dependent. Also, the amount of radiant flux that is leaving per unit area of the plane surface is referred to as the excitance, also an important quantity. And we've seen this notation before. This is capital M, also wavelength dependent. And again, it's just what I just said, the radiant flux that's leaving per unit area. Both of those quantities are measured in units of watts per meter squared. And this is just a conceptual diagram of what I just now defined, the quantities for irradiance, basically values coming from all directions over this plane, impinging on this particular surface area here, and the illustration here for the quantity excitance is on the bottom of this figure. So the radiant flux that is exiting that particular area on the bottom. Radiance, which we denote with capital letter L, is an extremely important quantity in remote sensing. And as, again, we note by the subscript here, it is a wavelength dependent quantity that we measure in remote sensing. The definition of radiance is as follows, and it's kind of a complex definition, but it's important to go through it because this is an extremely important quantity in remote sensing. And that is the radiant flux per unit solid angle leaving an extended source in a given direction per unit projected source area in that direction. And it's measured in units of watts per meter squared per steradian. And you see the notation there, watts per meter squared per steradian. So there's an additional unit there beyond what we have with irradiance, and it's the steradian unit here. You can think of a steradian as basically a three-dimensional cone over which we are accepting photons and detecting that with our remote sensing device. Okay, and we're only interested in the radiant flux at certain wavelengths, the wavelengths that our sensor is sensitive to, that are leaving our projected source area, we denote that with A, within a certain direction theta, and with a solid angle omega. And that solid angle is basically referring to the units of steradians that I discussed previously. So this is the equation here. So it's our radiant flux over that angle omega, or solid angle omega, I should say, that quantity over A cosine theta. So this is an illustration of what I was just now talking about. What we see here is our solid angle omega, which again is our three-dimensional cone over which we are accepting photons with our remote sensing device. And we are interested in detecting photons emanating or being reflected from our projected source area here in the direction toward our sensor, right? If we have a remote sensing device like a multi or a hyperspectral sensor, we're going to be pointing that in a particular direction. And so one of the main things I want you to take away from this figure is that there is a directionality to the quantity of radiance that we don't have with irradiance. Again, it's that per steradian quantity that we have in the units of radiance. Again, we don't have that unit with the units that we have for irradiance. So if I have an irradiance sensor, this is typically going to be a spherical type of sensor that is going to be accepting and measuring photons that are coming from a variety of directions. Whereas with a radiance sensor, a sensor where we're measuring radiance, we're going to be pointing that in a particular direction that is measuring the radiant flux in various wavelengths coming from a particular direction. Right, and we're measuring it in the direction that we are pointing our sensor system. And that is why radiance is a very important quantity in remote sensing. This particular slide and the next couple of slides just gives a little bit more detailed information as to what a steradian is. I'm not going to spend a lot of time talking about these slides. If you'd like, and if you're so interested, you can pause this in the next couple of slides and read about steradians in a little bit more detail. In general, though, we can say that a steradian is an element of a solid angle, and steradians are a measure of the angular area subtended by a two-dimensional surface about the origin in three-dimensional space. And here is more information about steradians on this slide, which again you can pause and read in more detail if you're so interested. And again, here is further information about steradians on this slide, which you can pause and read about in a little bit more detail as well. But I will underscore on this slide that steradians are used when it is important to characterize the directivity or the directionality of electromagnetic radiation, which again is what we are doing when we are measuring electromagnetic flux in units of radiance. At the bottom of this slide, we have a simpler definition for radiance, which is the flux per unit area per unit solid angle from, onto, or through a plane. And here N is the normal to the plane in these various figures that we see above. So we see the scenario where we have flux emanating from a plane. In the upper right hand corner we see flux onto a plane, and at the bottom figure we see flux being projected through a plane. Okay, so we are now back around to this diagram that we looked at previously, which summarizes the various paths of radiance that is received by our remote sensing sensor system. And it basically details the energy matter interactions within the atmosphere, the study area, as well as nearby areas, and the path back up to our remote sensing device. So we will look at all of these paths of the electromagnetic radiation going from the sun down to the Earth's surface and on its way back up to the remote sensing sensor system. Before we do that, though, we should briefly discuss some radiometric variables that are important to the process. I won't go through all of these in a great amount of detail. I do suggest that you pause this slide and consider each one of these radiometric variables in a little bit more detail on your own, but I will briefly discuss some of them here. Firstly, again, we denote irradiance with a capital E, typically in remote sensing, and we do that here with the solar irradiance at the top of the atmosphere. Sometimes we abbreviate that as TOA. Again, that's in units of watts per meter square. We have the spectral solar irradiance, again at TOA. Here we have added a lambda, so there's a wavelength dependency. E sub d is diffuse sky irradiance. There's also spectral diffuse sky irradiance, so there's again a wavelength dependency that we're accounting for. We have global irradiance that is impinging upon the surface, and again there's a wavelength dependent version as well. Tau is our normal atmospheric optical thickness. Capital T sub theta is our atmospheric transmittance at angle theta relative to the zenith. Another important variable is the solar zenith angle, and that is theta sub naught. Theta sub v is the viewing angle of the satellite sensor. Mu is cosine theta. And there's various reflectances such as rho sub lambda. Of course, that's just the surface reflectance of our target, which is wavelength dependent. And if we have the sub n subscript on that same quantity, it's denoting that we have reflectance that is coming from a neighboring area. The neighboring area is an area that is proximal to or nearby our area of interest, but it is not our specific target of interest. And then we have some radiance values here. The total at sensor radiance, again, notice the watts per meter square per steradian units here. The total radiance from the target of interest back toward the sensor is L sub t. The intrinsic radiance of the target is L sub I. It's basically what we're measuring in situ with a spectradiometer, and L sub p is the path radiance that arises from multiple scattering.